Okay, so let's start talking about the mole concept. The idea here is relatively simple. Um, the molecular world is tiny, and we're going to talk about how tiny the molecular world actually is. The problem with the molecular world being tiny is we can't really count things very easily, right? Whenever we talk about a group of atoms, we have to have some way to refer to it because the numbers are just outrageous. And so we basically use this idea of a mole to kind of simplify numbers so we have some reasonable concept of how these things react, how these things work together. So let's just start with a couple ideas. So first of all, formula mass. So before we proceed, this compound right here, first of all, it's a covalent compound. This is, and this is just from experience, you wouldn't be expected to know this. I have a carbon in the center, and I'm going to mimic the exact same drawing here. I have a chlorine off to the right. I have a chlorine coming out. That's the green ball. And I have a chlorine going into the page. Okay, that's the one back here. All right. And then finally, I have a hydrogen up top. So this is the compound that we have created. So we can recreate this compound and as just stay simple. Okay, it's one carbon, it is one hydrogen, generally label the carbons, then the hydrogens, and then everything else in alphabetical order. CHCl3. Okay, so this compound is together. And what we do is we can say, well, we know how much each of these things weighs according to the periodic table. So I would encourage you to pause this right now and open up a periodic table because we are going to need one. In fact, I'm going to open one myself. So you're going to need a periodic table. I'm going to keep referring to it, and I'll try to keep telling you where I'm getting this. I'm using ptable.com. It's a really neat little site. But so yeah, open up a periodic table or grab one and let's take a look. So what I know is carbon has a mass according to the periodic table. So if I take a look at carbon, I'm going to see that carbon has an atomic number of 6 and it has a mass of 12.011. Okay, so what we're interested in is the mass. I have one carbon, so that carbon in and of itself has a value of 12.011. Remember, we talked about weighted average. So, carbon 13, carbon 14, these different isotopes. But ultimately, if you pick up a pile of carbon on average, the carbon atoms are going to weigh 12.011 atomic mass units. I have one hydrogen, and the hydrogen, according to the periodic table, is 1.008 atomic mass units. But I have 3 carbons, 3 chlorines. Okay, so those 3 chlorines are going to be represented by 3 times the mass of the chlorine. Chlorine is 35.45 atomic mass units. So what I'm going to do is I'm going to combine all of these things together, and I'm going to get an overall atomic mass. So 35.45 times 3 gives me 106.35 plus the 1.008 plus the 12.011. Again, I'm getting these from the periodic table. Let's see here. And I end up with 119.369. We'll just truncate it to 2, so 37 atomic mass units. So on average, that is what one of these molecules is going to weigh, 119.37 atomic mass units. Okay, so I've just simply combined together the chlorines. So here's my chlorine. I have added in, those are the 3 chlorines. I have added into this the 1 hydrogen. And then finally, I have added in the 1 carbon that I have to give me a total mass of 119.37 AMU, atomic mass units. So we're going to change things around a little bit. we are going to no longer call it an atomic mass unit. We are going to replace that with grams per mole. So what we really have is 119.37 grams per mole. And we're going to get into what that actually means, but that is the formula mass for this compound, CHCl3, 119.37 grams per mole. So, and we're going to talk about what that exactly means. Again, because it's per mole, it's per 1 mole. So this thing weighs 119 grams for every single 1 mole that we have. And we're going to get into what that is. So what is the formula mass of sucrose? So we're going to do this in class. And so there's a crazy looking compound here. And this is how you read these things. Every time that there is like a change in direction, that represents a carbon. So that's a carbon right there. This right here is another carbon because we're having a change in direction. That's a carbon because it changes direction. So changes direction, changes direction, changes direction. Don't worry about the different stereo bonds. They're just simple lines, okay? Changes direction, changes direction, changes direction, changes direction, changes direction. There we go. So these are all of my different carbons that I have present. And I think I've got them all, okay? So this is kind of a crazy compound. You don't really need to know how to do this. I'm never going to ask you to know how to do this, but at least not right now. This is kind of how chemists look at this stuff. So I'm going to count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 12 carbons. So carbon, and there are 12 of them, okay? Next up, I'm going to take a look at the oxygens, and I'm just going to highlight those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 oxygens, O11. In fact, I should do the hydrogens next, but I'm going to put this here, O11. Now we have to count hydrogens, and this is a little bit weird. Again, I'm never going to ask you to do this, but every single carbon should have a total of 4 bonds. If you're interested to know, otherwise just blank me out for a second. Every carbon should have 4 bonds. So 1, 2, and then every other bond that's not there is filled in by a hydrogen. So I have 1, 2, 3 bonds to carbon. That means it's missing 1 hydrogen that we can't see. This one has a hydrogen. This one has a hydrogen. In fact, most of these are going to be missing 1 hydrogen. This one has 2 hydrogens that it's missing. This carbon right here has enough, so we actually don't need to do anything. This one's missing a hydrogen. This one's missing a hydrogen. This one misses a hydrogen. And this one misses 2. Let's count all of the hydrogens that we have. And I'll do check marks of these. 1, oh, not that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And I think that's it. So H22. Okay. That is really what I care about. Just how chemists see things are a little bit different. This simplifies it. It looks like a mess because I've written all over it. But what we do have, sucrose is C12H22O11. So what is the mass? That's what I'm going to ask you. Okay. What is the molar mass, or what is the formula mass of this? So I do know that I have 12 carbons. I know that I have 22 hydrogens, and I have 11 oxygens. Okay, so what we're looking at is this is the mass on the periodic table of carbon. This is the mass of hydrogen. This is the mass of oxygen. So what did you get for a molar mass of this thing? Okay, so do that quick calculation. Pause it, do the quick calculation, and we're going to move on. So we're going to go over this in class. Make sure that we're on the same page. All right. So let's talk about ionic compounds. So ionic compounds look like this. So we have 2 things here. I have, this would be the positive ion, the green would be the negative ion, and they just kind of group together and they expand. So, when I had something like Ca2O2, we would simplify this down because those would be simplified down to CaO. Well, it simplifies down because what ultimately we have is some ratio, right? So I have two of, I have one of each. And so it simplifies down. It's not a 2-to-2 ratio, it's a 1-to-1 ratio. So very simple concept. But for this one, cadmium nitrate, so I have cadmium, and we know cadmium is +2, and I know nitrate is NO3 minus. So I need to make a compound out of this. So what we end up with is cadmium, and I have two nitrates, NO3, 2. So what that means is, same idea. I'm going to do 1 cadmium. So that is equal to 1 times the mass of cadmium. I have a total of, so this parenthesis right here, here means that this subscript is going to multiply everything inside of it. So I have 2 nitrates. So another way of looking at this 2 is basically to say, all right, I have 1, 2 NO3s. That's what that 2 is representing. So ultimately, how many nitrogens do I have? And this is the molar mass of nitrogen. I'll plug these in, 14.007 grams per mole. And cadmium is going to be 112.41 grams per mole. And then how many oxygens do I have? Times 15.999 grams. Oh, that was a weird 9 grams per mole. Okay, so plug in these two numbers here for nitrogen and oxygen, and then figure out the molar mass of cadmium. Okay, so that's how we deal with subscripts. How many nitrogens, how many oxygens, how many cadmiums, and then we multiply it out. Good. Okay, so pretty simple, straightforward for an ionic compound, but that's the idea. Just take the 2 ions you've got and figure it out. So now let's get into this idea of, why is any of this important? What do the numbers on the periodic table mean to us now? So Avogadro's number, and we simplify it as capital N lowercase, or capital A is a subscript. Avogadro's number in the mole. So Avogadro's number is 6.02 times 10 to the 23rd. We're going to talk about how massive that number actually is in just a moment. But Avogadro's number is basically like saying, if I wanted to count molecules or atoms or ions or anything, we are going to simplify it. So instead of me telling you to go and weigh out, 6.02 times 10 to the 23rd molecules of water, I can just simply say, hey, go and get 1 mole of molecules. And there's a reason that we count. We have to count these things, because when we start reactions, what we're going to see is the number of molecules is important. It's like a recipe, right? So if I said to you, all right, we need 2 eggs and we need 1 cup of flour, you can't go and weigh those things out. So we have to keep track of the numbers. And that's kind of what Avogadro's number does. So really, really simply, Avogadro's number is represented by the term, the mole, the idea of a mole. So 1 mole is equivalent to 6.02 times 10 to the 23rd. Because the molecular world is small, we need some number to kind of sum all of these up. So 1 mole is equal to 6.02 times to the 23rd. This is it's kind of the same thing as saying 1 dozen, or I shouldn't even say 1 dozen. If I asked you to get 12 or a dozen, we know anytime you hear the term dozen, I'm talking about 12. Okay. Something a little bit more, let me look this up. So if I asked you, okay, so if you're ordering paper supplies for a company, you're not going to say, I need 100,000 sheets of paper. Generally, the term ream equals 500. It's 500 sheets. So one ream of paper is 500 sheets, right? The reason that they do that is they don't say, all right, I need 30,000 sheets of paper. They just say, oh, I'd send me, 300 reams, right? It's much easier to fit. Yeah. It's much easier to simplify the numbers. I don't need to think in terms of individual stacks, individual pieces of paper. I want to say, send me this many, right? I don't want to say, hey, can you send me 480 eggs if you're a baker, let's say. You want to say, hey, can you go order, 12 dozen or 10 dozen eggs? It's just a way of making numbers simpler. They're easier to kind of maintain. They're smaller, and we want smaller. Smaller is good. Our brains work better when we're dealing with numbers that are reasonable, right? 6.02 times 10 to the 23rd. That's hard to fathom. So the objects part of this is basically 1 mole of carbon atoms. This part, the carbon atoms part, is talking about what we're actually talking about. 1 mole of carbon atoms is equal to 6.02 times 10 to the 23rd carbon atoms. 1 mole of water molecules is 6.02 times 10 to the... Again, the mole is referring to this number. So notice that 1 mole is referring to this number. 1 mole, 1 mole. And then we have, with that, molecules, atoms, ions. Doesn't really matter. We're basically just saying, by saying 1 mole, you're giving me a total number of objects, right? I could say 1 mole of bananas. It's going to be 6.02 times 10 to the 23rd bananas, right? So those numbers are important. So you can watch this video if you want, but just to give you an idea of how big this number is. 1 mole of red blood cells is more red blood cells than exist in every human on Earth. It's massive. A mole of boxes, a box of cereal stacked end to end would reach from the sun to Pluto 7.5 million times. That's how large this number is. On Earth, there are 7.5 times 10 to the 18th grains of sand, meaning even if you took every single grain of sand on Earth, you are still a 3, 4, 5 orders of 5. So that's 100,000 times off. You have 100,000 times fewer grains of sand than actual 1 mole. Okay. If you had 1 mole of basketballs, it's the size of the Earth. You could create a new planet the size of the Earth. If you had 1 mole of donuts, it would cover the entire Earth in a layer of up to 5 miles deep. So this is a massive number. I can't get that through your head enough. This is a massive number. On the other hand, 1 mole of water. So if you compare all those numbers to macroscopic, it's huge. But 1 mole of water molecules is 1 sip, 1 gulp of water at the fountain. So it's a massive number, but it's actually really small. I mean, in the molecular world, it's not that big. Okay, so let's talk about this. So this first one here, and I'm gonna do one example, and I'm gonna let you guys do the other. In fact, I'm gonna do the first 2. How many molecules are in 2.5 times, or 2.5 moles of C6H12O6? So we're always gonna do dimensional analysis for this. So if I have 2.50 moles of our C6H12O6, I want moles to go away, and I want to figure out how many individual molecules I have. Well, I know that 1 mole is equivalent to 6.02 times 10 to the 23rd molecules. Okay. Again, all I'm doing is setting up my units so they cancel. And I know 1 mole, these 2 values are equal. So again, because 6.02 times 10 to the 23rd is equal to 1 mole, this is like multiplying by 1, right? So if I'm multiplying by the same value, it's like multiplying by 1. So it shouldn't actually change what we have here. So moles is going to cancel, and I am going to be left with molecules of C6H12O6. Okay. And get used to doing this on your calculator. So you should be able to calculate, basically know how to do this on your calculator, because it's going to be important. So 6.02 EXP or EE23 times 2.5. I guess I said that backwards. 2.5 times times 10 to the 23rd. Okay. Wow. 3, 6, 9, 12, 15, 16, 18, and 21, 18, 23. So 1.51 times 10 to the 24th moles of, or molecules of C6H12O6. Okay, so there we go. It's a giant number. It's even more giant because we multiplied it, but there we go. So that's one way of doing it. Notice that I use molecules over moles because I want moles to go away. So how many moles of helium are contained in a sample of this many atoms? So if I have 3 times 10 to the 22nd atoms, well, I want atoms to go away, and I want to be left with moles. 1 mole is equivalent to 6.02 times 10 to the 23rd. Again, 1 mole is equivalent to that number. These two are kind of used. 1 mole of atoms is equivalent to 6.02 times 10 to the 23rd atoms. By saying 1 mole, by saying mole, I'm talking about that number, right? So in this case, it's 3 EXP 22 divided by 6.02 times 10 to the 23rd. So you end up with a value of 0.05. Atoms cancels, and we're left with moles of He. Okay, and there we go. So again, it's that idea that this is, again, equal to 1, because it's 1 mole over 6.02 times 10 to the 23rd. So again, that's flipped. Okay, so we should be able to convert back and forth to individual molecules, or basically going from moles to individual units. Again, atoms, molecules, ions, none of that matters. So how many atoms of calcium are there in 0.75 moles of calcium? How many moles of water are there in 5.22 times 10 to the 24th molecules of water? So convert one from first one to atoms, and then the second one to moles. Okay. So with that said, so we talked about molar mass. Molar mass is the mass in grams of 1 mole of a substance. So I already said, so we've already done this calculation, but the mass in grams of 1 mole of substance. So you're going to see this a couple of ways. So molar mass, by the way, molar mass, we usually see mm. The other ways that you can see it, a molecule, we would say molecular weight. Let's put that in parentheses, molar mass. Molecular weight, which is MW, or atomic weight, or atomic mass. You might see AM or AW, something like that. You don't really ever see that, actually, so let's not confuse you. So MM, capital MM, or MW, those all mean the same thing. Essentially, how much does it weigh? Look at the periodic table, right? And again, the molar mass is the sum of the atomic weights of the atoms in the formula, okay? And we're going to take a look at a couple of those. Again, grams per mole. So if I have water, again, just about water's about 16 grams per mole. Hydrogen, there are 2 of them. It's 1.00, but it doesn't really matter. 1 gram per mole. So on average, if I add those parts up, I have 18 grams of water is equal to 1 mole. Right? Or really what it is 18 grams per 1 mole. So if I give you 18 grams of water, I've given you 1 mole. If I give you 9 grams of water, I've given you half a mole. If you drink, I don't know, 36 grams of water, you've drank 2 moles of water, okay? So this is kind of the most important thing here. We are going to take a look at this conversion in just a second, but this is what we just did on the previous page. So if I want to go from number of molecules to moles, I'm going to use Avogadro's number, okay? I'm going to use Avogadro's number to figure out how many individual units I have, or if I have individual units, how many moles I have. In order to go from moles, and this, by the way, please become really familiar with this, because this is what we do all the time. We use molar mass to convert between those, because again, the unit is in grams per mole. Grams per mole allows you to do those conversions, okay? So that's the one on the left is the one we do all the time and know how to do the Avogadro's number and how to do that. But grams to moles is kind of the one that we use all the time. Whenever you do a conversion from grams to moles or moles to grams, you must look at the periodic table. Basically, what I'm saying is you have to have a molar mass in order to do that calculation. Okay. A lot of the times, I just want to make sure that you kind of put in your brain that going from moles to grams or grams to moles, you got to look at the periodic table to see what you're looking at. So what is the molar mass? So we're going to do a couple of molar mass calculations, and we've done these already. So what is the molar mass of lithium oxide? Okay. So lithium oxide, look that up or come up with a value. In fact, pause this now and I will have the value up, or I'll walk through it right now. So you should do this one. I think I need this anyway for, yeah, one of these other ones. So I think I am probably just going to skip through and do, let's see, do you want to do this one? Yeah, how many grams, right? Okay. So yeah, so lithium oxide, there are 2 lithiums. So 2 times lithium, which weighs 6.94 grams per mole, times oxygen, 1 oxygen, 1 times, I don't need to do the 1 is 15.999 grams. Oh, that's weird. There we go, 9 grams per mole. Add those 2 parts up. So let's see, what do we get? Everything here, 6.94 times 2 plus 15.999 gives me 29.879 grams per 1 mole, or grams per mole, okay? So what is the molar mass of dinitrogen tetroxide? So pause this and give that a go. Dinitrogen N2O4. Okay. Again, you should be able to, now I'm using a skill from the last exam, so you should be able to do these conversions. Molar mass. What is the molar mass of calcium nitrate? So why don't you do this calculation? Again, calcium is 2 plus, nitrate is NO3 minus. I need 2 nitrates for every calcium. So there's your formula. All right. So how many grams are in 0.85 moles of lithium oxide? So that was our original number. I have 0.85 moles of, and this time we're going to start writing out what substance we are actually doing. So Li2O. I want to convert into grams. I want grams on top, and I want moles on the bottom. Okay. And in fact, chemists typically just write MOL, by the way, so be ready for that. So we already did this calculation. We saw that right here, we know that 29.879 grams is equivalent to 1 mole. That means, I already forgot it, 29.879 grams per 1 mole. Moles cancel, and my unit is going to be grams of Li2O. Okay. So how many grams do I actually have? So I'm just simply taking that value and multiplying across the top. So 29.879 equals, that was wrong. So, oh, sorry, 0.8, my bad. 28 or 0.85 times 29.879. There we go, better. You end up with 25 point, well, 397. But of course, we round this to 2 sig figs because the original one has it. So 25 grams of Li2O. That's what you end up with. Okay. So you've already done calcium nitrate above. So how many moles are in 62.52 grams of calcium nitrate? Again, set your units up, grams. I don't even need to calcium nitrate. I'm going to set it up so grams cancels and moles on the bottom. What goes in both of those, right? Same thing here. Calculate the number of moles in 4.32 grams. So we're going from grams to moles. Same exact setup as the one above us. Okay. All right. Then we get to this part. How many molecules of CCl4 are in 25 grams of... So let's make a plan for this. So again, in order for it to go from grams to moles, I need to use the molar mass. So we have to figure out the molar mass of CCl4 and convert to moles. Okay. Once you have the moles, then we have to use Avogadro's number in order to convert to molecules. And that's it. So that's our goal. And I think that's a good place to stop. So we'll talk about percent composition and start talking about more of this stuff. But we're going to do a bunch of examples of this in class. All right. Good talk.
Boo. Keep going.